So today we are going to discuss about the probability of detection and false alarm. So first we have to consider the envelope detector in the radar system. So in this envelope detector we have to consider the IF amplifier, second detector and video amplifier. Consider an IF amplifier with bandwidth BIF followed by a second detector and a video amplifier with a bandwidth of BB shown in figure 2.3. The second detector and the video amplifier are assumed to form an envelope detector. What do you mean by the envelope detector is to reconstruct the signal what we are receiving from the receiver. That is one which rejects the carrier frequency but passes the modulating envelope. Here what we are at modulation side, we are mixing the input signal and message signal and carrier signal, and now what we are going to do after receiving the signal, we are rejecting the carrier signal and allowing the modulated envelope. So the video bandwidth BB must be greater than that of BF and IF bandwidth by 2 in order to pass the video modulation. Why we have to choose like this is to get the better modulation, to reject the noise and to reject the bandwidth. So now what we have to do is, when we are assigning the threshold level, we have to consider the probability of false alarm and probability of detection. So when the noise is entering into the IF filter, we have to be identified. The noise entering the IF, that is in terms of filter and amplifiers, are used interchangeably. Assumed to be a Gaussian with a probability density function given by probability of V equals to 1 by root of 2 pi epsilon naught exponential minus V square by 2 psi naught, where psi naught is the variance. If Gaussian noise was passed through a narrow bandwidth IF filter, one whose bandwidth is same compared with the mid frequency, the probability density function of the envelope R of the noise voltage output shown is a rise to be. So PR is equals to R psi naught exponential of minus R square by 2 psi naught. What is the use of this is how many targets we are missing. So where R is the amplitude of the envelope of the filter output. The above equation is the form of relay probability density function. The probability of noise voltage envelopes will exceed the voltage threshold Vt is the integral of PR valued for Vt at to infinity. In previously we have seen how we are detecting the minimum detectable signal in the noise. So here now what we are going to do, we are taking the probability of that voltages at Vt to R, Vt to infinity. So the probability that the noise voltage envelope will exceed the voltage threshold Vt is the integral of PR evaluated from Vt to infinity. So probability we have to take at from Vt to infinity. The R should be varied from Vt to and the threshold voltage what we have set to the infinity. From that we are going to get the probability density function. Whenever the voltage envelope exceeds the threshold, a target decision is considered to have occurred by the definition. Since the probability of a false alarm is the probability that noise will cross the threshold and be called a target. When only noise is present, thus the probability density of the false alarm denoted by Pfa is Pfa is equals to exponential of minus Vt square by 2 psi naught. The average time intervals between the crossing of the threshold by noise is alone defined as the false alarm time Tfa. So where Tk is the time between the crossing of the threshold by the noise envelope when the slope of the crossing is positive. So here when we are assigning the threshold level, we have to identify that the crossing amplitudes or noise or present signal. So for that, when we are taking the identity of that, if any crossing signal is a noise signal, that time we are taking the probability. So here already this we have illuminated before itself. So what now we are modifying this is we are assigning the threshold level and RMS level. So here the peaks, what is going to be taken, peaks which is crossing the threshold level has taken TK. In the time period of TK, how many amplitude fluctuations are crossed the threshold levels. Here by seeing it, I can see three thresholds, three amplitudes crosses the threshold level. According to the between that time, I am applying the probability functions, and I am taking the reference with the relay the probability density function. So probability of false alarms are defined as Prd&Pfa is equals to sum of k equals to 1 to n Tk by summation of k equals to 1 to n Tk. So here I am finding the probability of alarm to the total variation and the when the discrete values. So here Tk is the average by capital Tk by average. So you are going to get 1 by Tfa into B, where B is the bandwidth of the IF amplifier of the radar receiver, and the average duration of the threshold crossing by the noise is approximately reciprocal of the IF bandwidth from above equation Tfa. So Tfa is equals to 1 by Bfi exponential Vt square by 2 sin naught. So next what we have to do, we have to consider the probability of detection. First we find the probability of false alarm. How many false alarm we are getting in a particular time, that is noise signals which are crossing to the threshold level. Now what we are going to do is probability of density detection. Consider a sine wave of amplitude A to be present along with the noise at the input to the IF filter. The frequency of the signal is the same as the IF mid-band frequency f of IF. The output of the envelope detector has a probability density function. So PS of R is equals to R by sin naught exponential minus R square plus A square by 2 sin naught, I naught into RA by sin naught, where I naught of Z is modified Bessel functions of 0 order and argument of Z for a large Z as I naught of Z. So where the signal is absent, A is equals to 0, and above equation reduces to the probability density function of noise alone. Here what I am going to do, I am detecting the minimum signal which can be present without noise. The probability that the signal will be detected is the same as the probability of the envelope R will exceed the predetermined threshold Vt. Probability of density Pd is therefore Pd of we are now what here also what we are going to search, probability of density function also we are searching from the minus Vt to infinity. So Pr of R into dr, that is integral of minus Vt by infinity R by sin naught exponential minus R square by A square by 2 sin naught, I naught Ra by sin naught into dr. Equation discussed above may be converted to the power by replacing the signal to the RMS noise voltage ratio with the following: A by A sin naught per signal amplitude by RMS value, signal amplitude by the RMS noise voltage is equals to root of RMS sine voltage equals to 2 sine power twice the sine power by noise power, that is a signal to noise ratio, root of signal to noise ratio. So that is we can write is root of square root of 2s by n naught. So this is about the probability of density function.